It gives me great pleasure to welcome you all to our small CUDA community. Before we start, I'd like to announce that we've joined the JetBrains user group support program. It means that during our events, I'll be able to raffle free licenses for most of JetBrains products. Of course, CLion is of particular interest to us. Although I use CLion for 5 years now, CUDA has been supported quite recently. That's why I'd like to give a short demonstration of the CUDA development process in the CLion. There is a CUDA executable project template in project creation window. So let's create one. I'm not quite used to the default formatting of CLion, but fortunately I can provide a CLang format file. It is sufficient to copy CLang format file in the project directory and then switch CLion to CLang format. And after that, I can reformat the whole file. Okay. And after that, let's write our first simple kernel. So, as you can see, CLion auto-completes triple chevron calls, as well as CUDA runtime API. But I can't quite recall the proper order of arguments in the elapsed time measurement function. So let's check how CLion can help me here. And here I can see the arguments order. Okay. But most importantly, CLion manages to autocomplete CUDA intrinsics, which I find most convenient. Or any other LDG. Okay, so all of the refactoring capabilities of CLion also works here. For example, I can rename our test kernel or change its signature. It is also possible to find all kernel usages. But we have one here. So that was some of the advantages of CLion. But I'd like to concentrate on some of the issues. For example, you can change the default debugger to CUDA GDB, and it'll work just fine in the host code. Here you can see states of the variables or evaluate expressions. By the way, autocomplete also works in GDB console. So let's turn on memory check. Unfortunately, we haven't caught the exception in our simple kernel. And unfortunately, there is no way to see variable states inside the kernels. I'll share a link to the issue, and I suppose it's our role to show developers of CLion that it is important. So please follow those links and vote for the issues. Anyway, let's move to the last issue that I'd like to demonstrate. If you are experiencing syntax highlighting problems, try to create a version file in the CUDA directory. It shall look like this. And that will be all of the demonstration. If you have any questions, I'll be glad to answer them after our speakers talk. What regards the raffle, I'm going to share an email in the chat. So please send me your name and use this event name as a subject. Shortly after the event, I'm going to raffle the license and send it back to the winner. And I am particularly delighted to welcome our speakers today. John Owens is an author of well-known course, Intro to Parallel Programming. I suppose that we are to hear the most exciting talk. But before we start, I'd like to discuss a few organizational questions. I'll be recording this presentation, and I'm going to turn off the recording as soon as the presentation ends. So please discuss any CUDA-related questions afterwards. Our meeting will last as long as we have subjects to discuss, so don't hurry to disconnect. And it will be all I wanted to say, so please join me in welcoming John Owens.
Good morning. Good morning my time. Sound okay? Can I get a thumbs up? Great. Okay, well, thank you for having me. I'm delighted to talk about this topic. This is something personally I really enjoy. Our research group has a pretty long history of working on data structures and how those data structures can be mapped to the GPU. So I believe we have 5 different projects I'm going to talk about today. What I'm going to aim to do, though, is less, I'm going to spend 10 minutes on each of 5 data structures and more talking about sort of the big picture of the things that we have learned from building data structures. I've only got maybe a slide each on the data structures that we actually built, but this is just a really interesting intellectual topic. And it's a great collaboration between those of us that are systems people, which are generally my grad students and me, and theorists. And so our collaboration there is with Martin Verrick-Colton at Rutgers. And so there's at least a couple of my co-authors that are on this call right now. So if you guys stump me with any questions, I'll have them jump in. But very happy to be here, and I'm going to get started. Okay. So the first question is, why data structures? Why is that a topic of interest? So in general, if I could sum it up in one sentence, I'd say that what data structures do is organize sparsity in some sort of way. And we're really interested in sparsity. I think many of the most interesting problems in GPU computing involve sparsity in some way. Dense problems usually map fairly straightforwardly to hardware architectures like the GPU, but once you get to sparsity, it takes a lot more thought and effort and so on. And so for those of us pursuing research problems, these problems are particularly interesting. And so many of the modern big data problems that we're looking into will not scale as we go to larger and larger dense representations, and we have to move into sparse representations to move forward. So for instance, our research group does a lot on graphs. And so the size of these graphs are such that we absolutely need sparsity to represent them. The other thing is that as you're learning to program, you have a particular toolbox of techniques. And so if you're programming in C, you can just pound include a bunch of, say, data structures from the standard template library, and they just work, right? You can say pound include map. You can then use standard map, and you don't really have to think about it. You know that it's a reasonably efficient implementation and well-tested and so on. And we don't really have that equivalent in the GPU world. The number of data structures that we have that are built in to some extent are just, vanishingly small. And so we found it to be a really interesting research problem to think about what these data structures should look like. How do we build them in particular? And so what do we actually want to do? So one thing that we want to do is have a data structure that represents some sort of pile of data, and we would like to query into that data structure. Okay, so this is a read-only modification. We don't have to worry about changing the data structures. This is a little bit more straightforward. But the kind of questions that we'd like to ask are, is this key in the data set or not? Or is this key probably in the data set? And we might have some trade-offs. We're willing to deal with a little bit of fuzziness in terms of the quality of that answer in exchange for another desirable property like density. We'd like to be able to do searches. We have key value pairs, and we'd like to be able to say, hey, given this key, tell me the value that's associated with it. We'd like to potentially do a successor query. Given this key, what is the next key? And then range. So this is, given these two keys, what are all the keys in between them? Okay, so the earliest GPU data structures were of this type, generally read-only, but most of the work I'll talk about today also is interested in mutating data structures. So once we have built a particular data structure, then we'd like to change it after we've built it. So that might be inserting new data, replacing data that's there, or deleting data. And so we have a couple choices on the way that we could do this. One thing we could do is just throw everything away and start over. Okay, rebuild the whole thing from scratch. But in general, we would like to have updates to the data structure where the cost of the update is proportional to the size of the update rather than the size of the entire data set. And so you expect that if you're programming on a CPU, you expect that if you're going to insert a new key into a map, you don't pay the cost of the size of the map, you pay only the cost of the size of the update. And so this has been one of our goals in building what we call dynamic data structures, this idea that you can change them on the fly. Okay, and the third thing we want to do is we want to be able to build the data structure from scratch. So for instance, the initial build that we're going to want to do, maybe we're going to get a list of data and we want to turn it into this data structure. And so we call this a bulk build, this idea that you have all the data not in a data structure, you want to put it into the data structure that you care about. We're also interested in general in doing sort of incremental builds. People talk about streaming kind of applications where new data is streaming in all the time. You have a social network, for instance, and new friendships are established, and you want to be able to have those be reflected in the data structure. One concern we've had in doing this work is it's a little bit unclear what the canonical use cases are for these incremental builds. I mean, I'm sure you can think of some off the top of your head, but it's surprisingly hard for us to put our finger on specific use cases. So one that our DARPA sponsors told us about is, they like to do what's called add and age, this idea that you're constantly streaming in new data, you're adding this new data as you come in, and at the same time you remove the oldest data. And so that keeps the size of the data structure relatively constant. So I'm very interested in hearing about your applications and what sort of uses you would do for streaming incremental kind of applications. Okay, so why is this hard, right? So why is this a challenging problem on the GPU? So first, there's some data structures where you just say, you know what, this is this really serialized data structure. It has beautiful properties if you're running it with serial code. But if we look in doing it in parallel, it's just not really a good fit for the GPU. So we're obviously not looking at that. The second problem is we see data structures that might be interesting in a parallel sense, but when we look at how they're actually described, it's very difficult to think about how to easily parallelize the way that they are described. So for instance, we might have some sort of tree structure and you go look in the textbooks about how this tree is maintained, and all the algorithms that they're going to talk about are these serial algorithms where you descend the tree, you insert an item in, you split the tree, and then perhaps you rebalance the tree. And all these are expressed in general in serial terms. They're rarely described as the kind of operations that we would like to do that are more bulk or parallel operations. So some of the challenge is to take those data structures that are described serially and figure out, what are the semantics, what are the operations we need to do if we're doing parallel operation on them. And by parallel operation, generally what we mean is we have lots of independent items that we would like to act on at the same time. Many queries, many insertions, many updates, that sort of thing. Finally, you have some data structures that are described in parallel, and that's interesting on the CPU. But when we dive into their implementations, the levels of concurrency that we see on the CPU might have, 8, 16, 24 cores, but that's a very different scale of concurrency than we see on GPUs, where we have hundreds of thousands of threads that might be resident at the same time. And so for some of these algorithms, they don't scale to that level of concurrency in the way that we would hope. And so that often requires new approaches as well. So these are all big challenges. And so I'll tell you how we address some of them as we move on in the talk. Okay. So I kind of assume that folks here are fairly familiar with GPUs and how they work and what the programming model is and how it intersects in the hardware. But I'm going to take a minute to describe that anyway, just to make sure that people that are a little less familiar might be able to, pick up on the terminology I'm going to use and at least have a big picture of how the GPU works. So our idea is on the GPU, we are going to write our code as a series of kernels. A kernel is a program that runs on the GPU. And these kernels are run on many threads at once. And we organize these threads in the following way. So kernels run over what we call a grid of thread blocks. And each block is a block of GPU threads. Each of these blocks, when we launch them, need to be independent. They can run in any order. The hardware chooses the order that they're actually going to get to run in. And these blocks are mapped to different cores on the GPU. NVIDIA calls these cores SMs, streaming multiprocessors. So you as the programmer get to specify both the dimensionality and the size of these grids and these blocks. There's an advantage in having threads within the same block in that they can communicate quickly through a local shared memory. But different blocks do need to be independent. They don't really have a straightforward way of communicating with each other. Now, within one of these SMs, we have SIMD style hardware. So 32 threads are going to run in lockstep at the same time. And we're going to turn out to use that a lot in this work, this idea that we have a warp of threads that's going to run in lockstep. And that's sort of the hardware atom that's inside each of these SMs. I'm going to say a sentence that hopefully it's going to make sense to you because but if you get this, then you really understand the GPU programming model, this idea that we launch a grid with lots and lots of blocks. And I want you to think that each of these blocks is a virtual SM, right? So we can launch hundreds of thousands of blocks. We've only got, 100 SMs, and the hardware takes care of mapping these blocks to SMs in an efficient way, right? So you think that you have an infinite number of SMs and the hardware is responsible for mapping your blocks to those SMs. Now, when we get down to this warp idea, it turns out that the memory system of a GPU is constructed so that you would really like to access the memory system a warp at a time. You'd like to make big chunky accesses into the memory. And so if each thread within a warp goes to memory and accesses a neighboring location, you get the most out of the memory system. And the term we use for those style of addresses is called coalescing. And so because these threads run in lockstep and because they really prefer these coalesced accesses for high performance, you try to avoid a couple things. One is you try to avoid threads that are neighboring that diverge in their execution because the hardware can only run one side of a branch at a time. So you'd prefer all threads to run in lockstep and never branch away from each other. And you'd prefer that threads go to neighboring places in memory and have these coalesced accesses. And both these things are important for high performance, and they're important in the way that we build our data structures. I'm watching chat, so if you want to drop any questions into Zoom chat, I have a lot of experience with weaving that into my lectures, so hopefully if you have any questions, I can clear them up along the way. Okay, so there's been a significant set of data structures that have been built over the last 15, 20 years of GPU computing. So let me outline just a little bit how I put together a taxonomy of GPU data structures. Okay, so the first set of data structures that were ever used on the GPU generally were built on the CPU. So the idea is data structures are complex to build. We don't have great algorithms to do them on the GPU. So what we can do is build them on the GPU, build them on the CPU, transfer them to the GPU, and use them there. So that's sort of our first taxonomy. What we're interested in is data structures instead that are built on the GPU. And then we have a couple categories. One is that we have data structures that are static, that you build them once and you never change them. And so some of those are general purpose and some of them are domain specific. And what I'm not really covering in this talk at all are the ones that are static and domain specific. But for instance, if you're building data structures to do ray tracing and you're trying to do this at real time, generally you rebuild these data structures every frame from scratch. There's some small exceptions, but generally this is a strategy you do. So you might build, say, a spatial data structure like a BVH tree to handle all the geometry in your scene. And so there's some really wonderful work by Tero Karras. This is one of my favorite papers in GPU computing, how he is building basically tree type data structures statically on the GPU. It's really just a beautiful piece of work. Okay, so, but now I'm going to go through some interesting data structures and what we think about when we're building them. And so all the data structures that we build involve some trade-offs. We would like to be able to balance several things when we're building these data structures. And this is interesting from an academic point of view because it means that we might have applications that need particular performance in one of these aspects and we don't care about another one. And it gives us the opportunity to build lots of interesting data structures that fill different places in this space. So the primary things that you're trading off when you're building these data structures are query time, lookup times, construction time, how long you build it, and how much memory you use, right? So that's if you take the amount of memory you actually use to store things in the data structure versus the amount of memory it takes to actually construct the entire data structure, we call that the load factor. So you'd like that to be as high as possible. And so maybe you're getting up into 0.8, 0.9 of the memory that you allocated is actually using data, and that's pretty good. Also, if you're handling dynamic updates, mutations, that might be a fourth axis that you might want to optimize over. So let me give you an example of the earliest GPU hash tables, which were built on the CPU. This was some really nice work done, well, at this point, 15 years ago. And so the authors were at Microsoft Research, and they were interested in building hash tables on the GPU. And they used a perfect hash function approach to be able to do this. So the trade-off that they made was it was very expensive to build these hash tables on the CPU. It would take seconds to minutes to do it. So it was not a real-time kind of thing. Then they would transfer these perfect hash tables to the GPU and have very fast lookups. And so this was an interesting approach in that building a perfect hash table is really a difficult thing to do. And so this approach would take sort of a hash table that almost was perfect. This is the hash table H here. And then it would have a second littler hash table that would be used just to tweak this enough to make it perfect. So figuring out the right hash tables there is what was expensive in terms of construction. But it was pretty cool that once you were able to do this, you were able to do some really fast lookups on the GPU. So in 2009, we decided we wanted to look at some hash table kind of problems, but we wanted to construct them on the GPU. And so this was the first work that used CUDA to be able to do these things. The previous work was not in CUDA. And we looked hard for the kind of approaches we needed to do that were really GPU friendly. And so what we arrived at was an approach called cuckoo hashing. And so I'll show a slide next to show how that works because it's really a beautiful algorithm. But these are the first hash tables to be built on the GPU. The nice part here is that this had really good best case performance. Basically, lookups were one read from global memory. And insertions were just an atomic exchange into global memory. These were uncoalesced, but it's a very small amount of memory accesses. And so usually this is a very good comparison for read and bulk build performance. Now, this is not a dynamic hash table. Basically, if you've built it and you want to add or change elements in it, generally you start over and you rebuild the whole thing from scratch. So the limitations of that are what led to the work I'm really talking about in this talk. But let me show you how cuckoo hashing works and why it's a cool thing for the GPU. Okay, so I got 4 items over here that I would like to place, 4 different colors. And what I do is I set up some slots where they can go into my hash table. All right, and I'm going to take those slots and I'm going to divide them into 2 tables, right? One table here and one table here. And then I have a hash function that's associated with each of these 2 tables. So H1 is associated with the first table. H2 is associated with the second table, and I compute a hash function for each of these items. Okay, so far it kind of looks just a normal hashing approach. Sure, there's two tables, but it's a normal hashing approach. The concern that you have is what happens when two items want to go into the same slot. What do you do when that's the case? Now, typically the way you handle this in the CPU case is you do chaining. You can put two items in the same slot just by having chains, but it turns out having individual chains of items is a really bad idea on the GPU, right? There's a lot of memory accesses. There's some significant load balance kind of problems, and there's some concurrency issues with putting those together. So we prefer not to do that approach. And instead, what we were using this is cuckoo hashing approach. So I'm going to show you how that works. So what we do is we have each of these items here. We look at hash function number 1 and we say, okay, where do you land in table number 1? And everybody tries to place its item into table number 1. And some of them are going to succeed and some of them are going to collide and fail. So the ones that succeed, we sort of put to sleep. The ones that fail, we say, okay, now we're going to try to place you into table number 2, right? So now we use hash function number 2 to place you into table 2. Okay, and again, some of them might fail. Okay, so then what do we do next? So here's the cool idea about cuckoo hashing. This idea, now we're going to go back to table number 1, and we're going to try to place into table number 1. But here's the trick. We will place in table number 1 and kick out the item that's already there. Okay, so this orange item popped over here into this slot, and now it kicked out the item that was already there. And now perhaps we try to place this item, and we go to hash table 2 now. We use hash 2, and maybe it's going to succeed. And so there's sort of these rounds where you're constantly kicking out items that are already there, and perhaps these shuffle themselves up so that you can end up filling up these hash tables. And so there's some nice probabilistic guarantees on this, all backed up by theory. But the nice part about this is that lookups are order of 1. If I'm looking up an item in these tables, I only have to look in table 1 and table 2, and I have a constant number of tables. So lookups have a constant time. And so most of the time, hopefully I'm going to hit in the first place that I look. That would be awesome. And so then lookups end up being very quick. And if you have, you can trade off space versus time. If you have more space in your hash tables, you're going to converge a little bit faster. You're going to hit more often on your first hit, and maybe your insertion and lookup times are going to be a little bit better. Okay, so this is cool. This is generally what people use. We have an open source implementation of this. This is generally what people use for comparisons. It's a nice technique, and it's generally pretty fast. Okay, but it's not dynamic. Right? If I have a whole bunch of items after I've already built the hash table, there's no guarantee they're gonna work. So generally what you do is you start over. So our interest in the work that I'm going to talk about today is how do we do things dynamically? How do we have hash tables that we can continue to add things even after we've built the initial data structure? And make the cost of that proportional to the size of the updates as opposed to the size of the entire data structure. Okay. So the baseline data structure that we use for comparison is something very simple and supported well by CUDA, and that's a sorted array. So if you're a theorist, you think about using a sorted array as a data structure, and you think, there's some really bad things about that. But it turns out on a GPU, a sorted array is both simple and reasonably fast, right? If you want to do queries into a sorted array, you can do a binary search. If you want to do a batch of insertions, then you have your batch of insertions, your sorted array. You can merge these two things very efficiently if both arrays are sorted, right? That merge is very fast. If you want to delete a bunch of things from a sorted array, then you just do a filter. And again, that's very fast too, okay? So binary search is, order log n. You don't really want to pay that, but it's not terrible. And everything else is definitely fast, has really good CUDA implementations. So, if you're just sitting down and you want a quick and dirty data structure, you can do a lot worse than a sorted array. And so we want to build something that's better than a sorted array, but sorted array is pretty decent baseline. So what we did build was 4 data structures. And these data structures aim at different points in the data structure spectrum. So For instance, if we want to support range queries, then there are certain data structures that will support that and certain data structures that will not. A hash table, for instance, is not going to support a range query, but other data structures might. So I'm going to talk about each of these just on one slide each, but I'm mostly concentrating on some of the big picture issues that we ran into. So what we looked at was a log structured merge tree, a B tree, a quotient filter, and a hash table with which we built linked lists and with which we ended up building dynamic graphs. And I'll talk about each of these individually. Now, one of the challenges of this work is a chicken and egg kind of problem. So, we decided we want to build GPU data structures, but there aren't really applications that use GPU data structures, mutable GPU data structures. And the reason people haven't built these applications is because there are no GPU data structures that are mutable. And so you have this chicken and egg problem of nobody's building something because there's no applications for it, but there's no applications because nobody's building anything. We hope to benefit to break this cycle by just building the data structures. And once the data structures are built, we hope that other people will adopt them and use them. And we've done that ourselves, say with our graph work. But we hope that as we have published these and open source them, that they will serve as a launching pad for people to use them and say this isn't good enough, and we or others can improve the work that we've done. Okay, so I'm going to talk about a few of the design decisions that we have here. So one of them is you want to update these data structures. The whole reason we're building them is to handle these dynamic updates. What is the scale of updates that we're talking about? So I have a big data structure out there and I want to insert some stuff. What if I'm inserting only a handful of items? Okay. In that case, we're not going to use the GPU very well. We just probably don't have enough work to fill it up. Maybe in that case, we have to fall back to a serial case. It's not going to be theoretically fast, but we might not care, right? It's just so few items to insert that the efficiency of it isn't so important. Now, on the far other end of that spectrum, we might want to update a ton of items, right? We've got 10 million items in our data structure, and we want to add 10 million items more. What we might want to do there is rebuild the whole data structure from scratch, right? In this case, the update size is the same as the data set size. Generally, it's probably faster to do just a bulk rebuild than it is to do incremental updates in this case. But the bulk rebuild is actually potentially a really interesting parallel problem by itself. So the kind of stuff that we're really targeting here are things that are between these two cases, where there's enough stuff to put in that actually keeps the GPU busy, in which case we really do care about efficiency. But there's not so many things that we should be falling back to bulk build. And so generally, as we're evaluating this work, we look at a very wide range of insertions and be able to say, look, here's the band in which you should do incremental stuff. Here's the band in which you should do bulk things. So here's another question that we had when we started building these data structures. So if you've got a big modern GPU, it takes lots and lots of threads to stay busy. So the kind of scale updates that we're generally considering as we're designing these data structures is that we have lots of threads that are active, and every thread has something that it would like to do to this data structure or with this data structure. You might have 100,000 threads. Each of these threads wants to do a query, or some of these threads want to do insertions and some of them want to do deletions. But basically we have lots of threads, each of which has an individual operation they want to do on the data structure. We hope this is a good use case. Again, since we don't really have applications, we don't really know. And I'm interested to hear about your use cases because this is an active discussion that we're having. But in general, this is how we think that people want to use widely parallel data structures. So when designing, we can think about this giant chunk of work in a couple different ways. One, we can think about, okay, when we actually implement this under the hood, do we have all these threads? Are they all going to cooperate doing one big thing? Or do we think of them more as 100,000 threads, each of which is completely independently running, right? Do they cooperate or not, right? So we've got this big chunk of data we're adding to our data structure here. Do we treat this input as one big giant chunk of data? Or do we treat it as 100,000 individual chunks of data? And we have data structures that have been on both sides of this. like it's viable to build them either way. And different data structures, we do treat them in a different way. So one of the strategies we developed to address these is how we think about the relationship between threads and warps and what that means in terms of our operations. So when we started doing this work, and generally the CUDA model says, you've got lots and lots of different threads here. They're all active at the same time, and each thread is independent, right? You write one program that runs on one thread, and different programs can branch in that thread any way that they want. So you might have one thread doing insertion, one doing searching, one doing deleting. And so traditionally, you can write code like this, right? So you've got this little switch statement up top. Am I doing this or this or this? So the atom that we think about here is an individual thread, right? That is an individual piece of work, and that's what we're focusing on. But if we do that, we have some real downsides. So there's a couple issues here, because what actually happens in the hardware is that we have a warp of threads that all run in lockstep at the same time. The size of that warp is 32 threads. So if we've got 32 threads that are all running in lockstep and they want to do different things, it means that our threads are diverging and we potentially lose performance because this warp can only go down one side of a branch at any given time. So in our picture over here, we might have this guy's inserting, this guy's searching, this guy's inserting, and so on. And the hardware is sort of bouncing between these different operations as it tries to get all these threads to the finish line. So it's not running at full efficiency when we do that. The second issue that we have is each of these threads is potentially going to a different place in this data structure. And so we have massive uncoalesced memory accesses. Basically, all these threads want to go to different places in the memory. We really prefer that not to happen. We're not making the most out of our memory system when we do this. So what we said is, rather than thinking of the fundamental atom of processing as being a thread, we will instead think of it as a warp. Okay? This idea of having 32 threads gang together, running in lockstep. And so what we do is we take this list of 32 different operations for 32 threads, and we sort of turn it on its side. And so rather than having 32 threads that are each doing 32 tasks at the same time, what we do is we have a list of 32 items to process, and we take them one at a time. We're basically serializing the 32 tasks that we need to do among a warp. So when we have 4 items here in this picture, first, all 4 of these threads cooperate to do an insertion. Then they all cooperate to do the next insertion, cooperate to do a delete, cooperate to do a search. Again, we're serializing here, but this has some advantages when we do it this way, right? So if you write it right, now you've got 32 threads cooperating to do an insertion. We can write it in such a way that they're all going to suffer from no branch divergence, right? They're all going to be cooperating together. If we design our data structures right, when they go to memory, they're potentially going to memory all for a big chunk of memory and using that whole chunk of memory when they do. And so we're not going to have any memory divergence either. And CUDA gives us really powerful primitives, intrinsics that allow us to communicate between threads in a warp very quickly. So we can take advantage of that. Now, it absolutely requires that the data structures that we design are designed around this idea of doing warp-wide operations, but I'll show you some examples of that shortly. Okay, so now I'm going to actually talk about the data structures that we built. All right, so the first one that I want to talk about is a data structure that supports dictionary queries. So, a membership query or a key value lookup, but it also supports range queries. We want to be able to say, hey, tell me all the keys that are between this lower bound and this upper bound. And so here's what this data structure is going to look like. All right. So what we have is a number of levels of this data structure, starting at 0 and going as high as we need. And each level is twice the size of the previous level. So this is the log structured part. So level 0 has 1 chunk of data in it. Level 1 has 2 chunks of data in it. Level 2 has 4 chunks of data in it, and so on. Now, a level is either completely full or it's completely empty. So for instance, in this left picture here, we have 5 chunks of data that are currently stored in our data structure. And so by a binary number kind of property, you know that that means that level 0 is full and level 2 is full and level 1 is empty. Now, what happens when we want to insert new things into this data structure? All right, so we have a new chunk of elements that comes into this data structure. Okay, so the first thing we do is we take that chunk and we say, hey, we'd like to put it in level 0. Ah, man, level 0 is full. Okay, so what we're going to do is take this new item and the item that's already there, and we're going to merge them together. So we've stored these as sorted lists. We bring in a sorted chunk, and then we merge this sorted chunk with this sorted chunk, and then pop it up to the next level, right? So we've merged these two together, we pop it up to level 1, and now level 0 is empty, and level 1 is full, okay? So it may be that when you merge, it cascades all the way up, but eventually you're going to reach a stage where there's empty space and it's going to land there. And there's again, some nice guarantees on what the amortized cost of insertions are. But insertions here are very fast because all you're doing is merges, and you can make a sorted merge very fast. And in this data structure, operations are coarse, and that all the threads are cooperating to insert a chunk at a time. Okay. So we also looked at a hash table-like structure. We wanted to build dynamic hash tables. Hash tables do not support range queries, but they're really good at point queries. And so we wanted to talk about what a hash table looked like that would support dynamic operations. And so traditionally, the way you do this in a CPU is you have linked lists per bucket. But it turns out these are really bad for GPUs, right? If you insert an item, have a pointer to the next item, pointer to the next item, and so on, it's really space inefficient because you have lots of space that are taken up by these pointers. You have really bad locality. You don't have this sort of coalesced behavior. Your branch divergence is bad. It's not the way that we want to think about it. So the insight here is that the right atom, the right size of the fundamental thing in this data structure is not just a regular linked list with a key value pair and a next pointer. It's instead a warped sized list that we call a slab list, right? So we've got lots of items in the list and then one next pointer. And each of these items has a key, metadata, perhaps a value, and so on. And so our slab list doesn't just store one item per slab, it stores many items per slab. And then we can cooperate along a warp to be able to do the operations that we need to in this entire slab. What is a slab hash? It's just a traditional hash table where you have a bunch of buckets, and each bucket has one or more slabs that are linked list together. Okay, so what's actually in a slab? Okay, so we say each slab is the size of a GPU cache line. So it's one cache block. That also corresponds to having a warp with 4 bytes for every element in the warp. So what's actually in here, we have 30 data items and then 2 items for metadata and the next pointer here, right? So we might have multiple buckets in our slab list. And so that allows us to have a variable number of items per slab. Okay, we spent a lot of time thinking about memory allocation here because as you're inserting new items into this data structure, you have to allocate new buckets. And so we built a custom memory allocator just to allocate new buckets because it turned out memory allocation otherwise is a pretty expensive operation. Now, we used this data structure to build a dynamic graph. The idea that you have a social network out there and you want to add new people to this network and new connections to this network. And so traditionally, the way that this has been done on the GPU is for every vertex in the graph, you store a list associated with that vertex. What are my neighbors? Okay. And so when you do this, you have a couple of design choices to do. One of these design choices is I would like to store that list unsorted. And so then it means when you query into the list to say, does this vertex have this other vertex as a neighbor, you have to search the entire list, and that's very expensive. Okay. Now, the other choice you have is you say, hey, I want faster queries. Instead of storing the adjacency list as a unsorted list, I'll store it sorted. And then I can do a binary search in it. It's a much faster search. But then you have to always maintain this list as a sorted list. So as you're making changes in this list, you have to constantly keep it sorted. And that bookkeeping turns out to be very expensive as well. So we philosophically do not believe that list data structures on the GPU are a good fit for dynamic graphs. What we built was a graph data structure that would use, instead of lists, use hash tables to store adjacencies, right? And so we have efficient query and efficient update on our hash table. And this has considerably better performance than other dynamic data structures that use lists as their fundamental atoms. So we've integrated this into our Gunrock graph library, and we're actively thinking of cool ways that we can use this capability in real applications. Okay. So another data structure we wanted to build was a probabilistic data structure. And this seems pretty weird. Like, why do we want a probabilistic data structure? And so what you want to say is you want to give it a query and you want to say, is this item in this set? And a probabilistic data structure will return one of two answers. One is, it is definitely not in the set. And then the other answer is, it is probably in the set. Okay. So it turns out you can do this with considerably less space. And the canonical data structure that does this is a Bloom filter, which is a beautiful data structure. We compared against a Bloom filter in what we did. But our structure is called a quotient filter, and this is also originally built on the CPU. So the way that this looks is what we do is we take each key that we have and we hash it, and then we've got a bunch of bits associated with the hash value. And we take those bits and we divide them into two pieces. We divide them into the quotient part and the remainder part. And so then when we're inserting an item into the table, or we're looking for an item in the table, what we do is we figure out where is its quotient in this table, okay? And we try to insert it into the spot associated with that quotient. But the only thing we actually store in the data structure is the remainder bits, right? And the remainder bits are potentially smaller than the actual size of the hashed value, right? So we can save a lot of space by only storing the remainder bits. Now, then the question is, what happens when there's collisions? What happens when two different items have the same quotient? And so there's a lot of bookkeeping involved with what do I store and how do I cascade it down, right? We can have two items with the same quotient that are stored next to each other, and that's really the beauty of this data structure. But it gives you real space economy and good performance at the same time. Okay. And the final work that I want to talk about is a data structure that also handles point and range queries, but does so with a different goal. And this is using a B tree, right? So we would like, in this one, lookups to be done as fast as possible on this data structure. And so a B tree is a very classic data structure. It is something that should be amenable to parallelism. And the idea is it's just a tree, but each element in this tree has many descendant pointers. And so we size our intermediate nodes, not surprisingly, to be the size of a GPU cache line. And we're able to use this warp cooperative work sharing strategy so that when we work on a particular node, we're doing it with an entire warp at a time. One of the changes we made is a traditional tree is just a B tree is just a tree. We've added this idea of having side links. This is done by previous work. We didn't do it. But if you have side links so that neighbors on the same level of the B tree have a link to the next neighbor at its level, it turns out you can get away with less locking. And it turns out this is actually very, very important. What we learned from doing this B tree implementation is the thing that matters more than anything else, priority 1, 2, and 3, is reducing contention as much as possible. As you're inserting into this tree, traditionally, you have to lock things all over the place to make sure that concurrent insertions do not collide with each other and produce wrong results. So you do an insertion, you lock a bunch of the tree, you do all your bookkeeping. If you do that on the GPU, with lots and lots of threads active at the same time, then it turns out your performance just slows to a standstill. It's a terrible data structure if you do it in the classic textbook kind of way. So we add these node links. We do proactive splitting to make sure nodes are never actually full. You split sort of eagerly. We do latch-free reads, which gives us more work to do at the benefit of having fewer locks. Rather than having spin locks and things wait and have more contention, we start over when we fail, and it turns out that reduces contention overall. And so the difference between building the textbook B tree and the B tree we ended up coming up with after all these different design decisions was 3 orders of magnitude in terms of performance. It made all the difference to spend all of our effort to be able to reduce contention as much as we could. And the paper will give you a lot more details on that. The other fun thing about B trees is that in general, GPU caches are not always the most useful thing in the world. I think most GPU programmers treat caches as, hey, these things are convenient, and if we get a good speed up out of them, that's fantastic. But I have so little space per thread, it's hard for me to really take advantage of a cache, right? When you've got a few, megabytes of cache, but you've got 250,000 threads that are active at the same time, it just doesn't give you a lot of space per resident thread, right? And so it's hard for you to really be able to take advantage of locality. The B tree is a pretty friendly structure to caches. And it turns out that in our B tree implementation, we really are taking advantage of the caches. The high levels of the B tree really do get cached and reduce our aggregate memory bandwidth to main memory. So, on Volta machines, we were actually getting an aggregate bandwidth that exceeded the main memory bandwidth of the machine because we were getting pretty good cache locality in those higher levels. So we were happy to see that. So the B tree and the LSM, the log structured merge tree, should have very similar characteristics in terms of their functionality, but queries are the B trees optimize on queries, LSM optimizes on insertion. So as we expected, we'd have better B tree performance on queries, but it turned out for small batches, B trees were actually better in terms of insertions as well. So that was gratifying, not something we really expected from the theory, but it turned out we didn't need so many elements to fill up the GPU because we used this work cooperative strategy was potentially helpful there. And so for small insertions, our B tree actually performs surprisingly well. Okay, so I now have some big picture kind of issues that I want to discuss that are like elements you think about if you're trying to think about data structures in general, right? I want to design a new data structure. What are the things that I have to think about? Okay, so these are issues with hash tables that I think what we found are generally issues with all the data structures we built. So one is memory allocation. So we have a data structure, we allocate enough memory for it, we put it in the GPU memory, and then we add a bunch of stuff to it. And what that's going to mean is you need to allocate some more memory there. And GPU memory allocators are not as well developed as CPU allocators. If you're using CUDA malloc to be able to allocate new space, it's not very good at doing small allocations, and maybe your data structure wants small allocations. So Rapids Memory Manager is supposed to be a really cool piece of technology. We haven't really dug into that with our data structures yet, but I know there's a lot of interest in building faster, better allocators. What we built with our hash tables was a custom allocator that was only designed to do new slabs. And the problem with many allocators is you integrate it into your application and it takes up a lot more registers. When you have a lot more registers, you get fewer blocks or fewer threads that can be resident at a time, and you see a downgrade in performance because of that. So we built a really efficient memory allocator that only cost us 2 additional registers, and that was necessary for us to be able to get the rates that we did. Another big picture issue with the hash table that we built is that ideally the number of items we have per slab basically almost fills up a slab, but doesn't spill over to a second slab. And so as you insert more and more items, the ideal number of items sort of falls away, and then you end up doing chaining across many slabs, and your performance is going to fall. So if you're in the CPU world, what people say is, hey, stop and rebuild, right? You don't have to do that very often, but that's what a high performance data structure library will do if you don't know how many items are going to be in your data structure. Is this a viable data strategy? It's basically a garbage collection step. It's not the sort of thing people do on GPUs very much, right? How do you sort of measure when it's time to rebuild and do this rebuild? It's not the sort of model that we usually have when we think about how to build GPU code. We also are concerned, data structure-wise, with what happens when you have scale-free kind of graphs where some items have only a tiny number of neighbors and some might have thousands and thousands. And a one-size-fits-all hash table is maybe not the right solutions there. So we're interested in looking at distributions of work that might be, far from uniform. Okay. Another concern that we have is, how do you actually access these data structures? What do programmers actually want? When I say pound include GPU hash or GPU map or whatever it is, what is the programming model for that? So the programming model that we were assuming is, hey, you've got 100,000 threads resident. Each of those 100,000 threads has one small task to do, go. Is that really what programmers want? Right? We don't have an alternative to that, but if we had an alternative to that people said, this is the way I really want to use it, are our data structures really the right one? We're not sure. I think this is an unanswered question. Another big picture question we have is, as we move from a serial data structure where the semantics are very well established because things are serialized, to a parallel world, what does semantics actually mean? Right? So what does it mean to put in a bunch of insertions as a bulk operation, right? How are those ordered, right? How do we handle what happens when you have 100,000 insertions you're doing into a data structure and two of them insert into the same key? What does the programmer want to do in that case, right? So what do we tell the programmer in terms of semantics? Like one thing we could say is, we can guarantee that if you order them from left to right, the one at the left is always going to win. We could say, hey, if you put these in, buyer beware, one of them is going to win, but we offer no promises as to what it is. Like we don't really know what programmers are going to expect here. And I expect as people build and use these data structures more and more, we're going to run into this problem of what these semantics actually mean. Another question we have is, if we have, say, a graph data structure, do we have different phases of updates and queries? So we've heard that some people structure their graph applications as far as we do this phase of update the graph with a bunch of updates. We're not going to do any queries. Then you sort of stop and you say, now we're going to make a bunch of queries into the graph. And then when we're done with those, we're going to go back and do a bunch of changes again, right? Are real application phased in this way? And if they're not phased in this way, then what are the semantics about having queries simultaneously with changes in the graphs? So we just need more people to use data structures and sort of give feedback as far as what we actually need. Okay, here's some of the stuff that we're thinking about going forward. One is to integrate dynamic graph data structures into shipping code. So this works already in Gunrock. We expect Rapids might be something that's going to be interested in doing dynamic data structures. And so we hope that our work will be integrated there. We're currently revisiting different classes of open addressing hash tables like Cuckoo and seeing, now that we've built a bunch of data structures, can we make these better? We think some functional programming data structures look really cool. Like they're more advanced data structures, I would say. And could we build those on the GPU? Like these functional programming languages ought to be pretty GPU friendly. Let's look at their data structures. We care a lot about workloads, and we built a lot of these data structures without really knowing what the workloads are going to be, but we'd like to work with people that have cool workloads. We think these data structures might be interesting being opaque data structures that are used in higher level languages that are not CUDA, right? CUDA, you really see into what the data structure is doing, but could we provide them opaquely to something that's higher level? And we think some of these design decisions we have motivate making some of these decisions at runtime. And what does it mean to have GPU runtimes? And what is the functionality they could do, and how could they help us manage and optimize data structures? So anyone from California, I want to particularly thank you for supporting the University of California with your tax dollars and your advocacy. Couldn't do this work without that. We've had some wonderful funders from NSF, DARPA, NVIDIA, Adobe, and lots of folks who've helped us out along the way. Thanks for your time.